Hi, yeah, cheers, thanks. So I'm Mike, and I'm here to talk about VanSpoof and F gear, which are two projects that I've built to reverse engineer some components on a proprietary e-bike to try and prevent it from going into e-waste. Yeah, so a little bit about me. I'm not a scientist. I'm not a professional. I'm an IT guy. I'm an enthusiastic amateur. And what I'm going to show today is how pretty much anybody with a bit of YouTubing, a bit of Googling can get all the way to producing some open hardware. So the bike that we're talking about is a VanMoof X3, which is the Apple of e-bikes, for better or for worse. Fully integrated, completely automatic. It does everything you'd ever wanted to do. It's the bike that you can give to somebody that doesn't want to ride a bike, doesn't want to think about it. If you want to get somebody out of a car, you can get them onto this bike and they'll just be able to get up and go. It's the perfect bike. It really is. It's got small wheels and it's got really low center of gravity, so you don't have to worry about wobbling when you get up to traffic lights and falling off it. It's got integrated lights front and back, so you don't have to remember to charge your bike's lights or remember to take them with you. It has racks front and back, so you can carry stuff. I mean, it's the most practical bike that I've ever seen. And the most important part for that, for getting just normal people onto it, is it has an automatic gear change. So like an automatic car, this will change gears for you as you ride. Unfortunately, it's incredibly fragile. The electronics in it go pop in a number of various different ways. It's connected, and so they pretty much did everything except reinvent the wheel on this bike. All the custom components and everything all go back to an actual one standard component that you can buy off the shelf, which is this hub gear that's in the bottom right in this photo. And that's an off-shelf part. That's an internal hub gear. The clever part they've built is they've built the electronic device that shifts you between your gears. The problem is yeah, this is very, very fragile, and the company went bankrupt. There are no spare parts. There's none left. There are people reconditioning them. There are people repairing them, but it is drying up, and it is getting more and more expensive to try and repair these things. These bikes cost £2,000 when they were brand new. The market for these parts is just getting harder and harder. So I thought, I'm a big dumb idiot. What about if I could just work out how it worked? So I cracked it open, and yeah, we'll talk about how I managed to get it working. So the first thing I built, and this is if I look familiar at all, Sid had me along to one of the show and tell videos on YouTube to talk about the spy brake inject. So this is a 4-wire monster in the middle circuit. It allows you to interpose yourself in the middle of a 4-wire signal. You can hook up oscilloscopes to the bottom. You can hook up scope analyzers to the top, and then you can pop off those jumpers, and that will let you route that board, the signals off that board, off into your own microcontroller. You can fiddle with the packets and then push them back in again. And yeah, so my background is I'm a woodworker, and kind of what happens in woodworking is if you don't have a tool, then you make a jig. And so this is the jig that I made to let me do the next step on the process. So here's the first step in the process. So I managed to get in between a working shifter and the bike, and now we're just puzzling it out. We've got these 4 wires. What do they do? What's on them? And how can we kind of pretend to be the shifter on the back of it? When I started this project, there was very little knowledge about what was actually happening in this communication channel. There was one chap on Reddit who reckoned there's 24 volts on one of the lines, and that was pretty much as far as the reverse engineering had gone at that point. So out with multimeter probes, found out, yes, between that yellow and black wires, there's 24 volts. But from blue down to black and from red down to black, there's 5 volts that at first you think maybe I've not got the probes held properly because it keeps dropping to 0. But then when you actually put the oscilloscope on it, you realize that it's actually, there's data signals going on there. There is actually something there. And so you've got 2 wires, 4 gears. What could possibly be going on there? You could have serial, I2C, CAN bus. It could just be using the 2 wires to give you 4 different signals for digital bits. But hooking up to a scope, there's something there. You can see for sure there's signaling, and there's very much probably a call and response style action. We've got some sort of frame of data going one way, and we've got a frame of data coming back. So it looks like a request and response. At this point, we don't know, is it the bike asking the shifter? Is it the shifter asking the bike? So that's where kind of we jump in with the spy brake inject. If you stick the probes on the same wire either side of your jumper and you pop the jumper off, then you will start to see, do I see the signal, lose the signal? How does the system react to the connection being broken in the middle? So does a packet get all the way across and then fail to come back? How does everything react? And so, yeah, what we found out was that, one of them is the bike, one of them's the shifter, and the order of it was that the bike is sending commands and then the shifter's sending responses. So we're getting there. So the next part is, pretty much the only reason I can get kind of anything done in this is by standing on the shoulders of giants. This is a project about using open hardware, using open software to develop more open hardware. So that board there is plugged into a Glasgow Digital Interface Explorer, so a crowd supply success story. I'm really only using it in the very, very most basic of its systems. Like, so here I'm using it as a logic analyzer, capturing the packets that are flowing back and forth. But here we go. So we now have packets, we have frames. We can identify. This is loaded up in GDK Wave, so a really good, fast open source piece of software to view these signals on. It's great. You can just take little slices to take your measurements of time. So what we find out here is that it looks like 1 bit is about 104 microseconds, which, if you're that kind of nerd and you're that kind of old and you work that into a baud rate, it's 9600 baud. That sounds like a magic number for people of a certain age. We're probably on the right track. The next step of it is we can see the request up front is about 8,000 microseconds. The response is about 7,000 microseconds. You probably can't divide 7,000 by 8. We're probably not looking at 8-bit bytes. But if you're the kind of person who said 9600 baud, then there's a framing called 8N1, which gives you 10-bit bytes, which then suddenly those numbers start to make sense. You divide it out. We're probably looking at a serial connection. We're kind of, it's all unraveling as we go along. And so at that point, I stopped, because I've probably got enough information now to build the hardware, even if I can't build the firmware and stuff for it yet, because we know the signal, it's just a 5-volt UART signal. So all we need is a microcontroller that has a 5-volt compatible UART. And so just going through kind of the goal for the project here was, I wanted to be accessible to as many people as possible. So single-sided surface mount board, you can just send it off to JLC. They'll send you one back in 3 weeks, job done. If you want to do it by hand, surface mount gets more difficult, but you can get, this is a TSOP 20 footprint, you can hand solder down to about that sort of size. So this is something that, if the tariffs start to hit you and you don't want to get manufactured in China anymore, as long as you can get the board produced, you can then hand manufacture it somewhere else. It's not out with the realm to make these by hand. The STM32 G0 is a great option for this sort of thing, particularly as a hobbyist, because it has very little extra stuff that needs to be set up. it doesn't need a crystal to run as its oscillator. It will just boot off itself. You just give it 3.3 volts and it will just rock and roll. And for our purposes, we don't need something like an ESP. We're not doing Wi-Fi or Bluetooth or Zigbee. We just want something that can kind of handle 5 volt through its GPIO pins. And that's what you get with these kind of the cheap STM. And they are cheap. They're not very much at all. So at that point, I had enough information probably to build my first prototype version. And so this is very much take a bunch of data sheets, slap them together in KiCad, and just rock and roll. And that was it. I mean, like I said, I'm not an electronics guy. That's a 7805 linear regulator, and it's jelly bean parts following the guidance in the data sheets. It's just the programming headers match the same layout that are on ST Discovery board. So if you've already got a dev board for any of the STM chips, then you can just cable it directly across. You don't need a special programmer. You've already got one as part of the dev kit. And the only other option I had on there was I stuck a little blinky LED on there so I could prove to myself that when the firmware ran, it actually did something without having to work out the rest of it. Rendered in a very pretty purple color because they were manufactured by Osh Park. And so while I was waiting for that to arrive, I moved on to the physical part of the project, which is the F gear. And so, as we said, the shifter itself only moves the internal hub in the middle. It doesn't. It's not actually really part of the shifting mechanism whatsoever. It's in the hub is where the shifting happens. The interesting thing is that this bike, because it's an e-bike, you're not as dependent on having lots of low-range gears to get you up a hill. If you struggle, you can rely on the electric motor to pull you up the hill. So I don't need to build a complete replacement for the original unit. I just need to build something that the bike thinks is a working one, and then I can fix it in place and fix it in gear. And so the community consensus, which is just like a bunch of angry guys on Reddit, is that third gear is the best kind of compromise between high speeds and being able to get away from a stop. And so this is just a 3D model of what would be replacing the interface to fix the bike in third gear, so that it doesn't ever kind of shift out as you're cycling along. It doesn't pop out of gear. It doesn't cause any extra damage to any of the components in your bike. It just lets you get on with it. And probably to the surprise of most people here, I'm one of the only few people here that doesn't own a 3D printer. And so I I just asked around on the social media for where would I get it printed? What's the options for 3D printing companies? And it turns out that when you do that sort of thing, really nice people respond. And so a chap called Mika in Germany said, "Don't bother going to a company. Send me the files. I'll print it. You pay for postage. I'll use it at the end of my spool of filament. It's fine. It would be waste for me anyway." And yeah, so like 2 weeks later, through the post, some guy's 3D prints turned up. Like, excellent. The problem is I don't have a 3D printer, so I don't know how to design for 3D printing. And so they were too perfect a fit. They were really tight. They worked. You could fit them on. You could make them all mash up. But because we were wanting to fix the bike in third gear, if it was first, you'd have it cranked all the way one way. If it was fourth, it would be cranked all the other way. But because it's third, it's an independent little position along the way. And so you have to drop that down onto the hub whilst slightly aligning this hub gear in a space that's getting tighter and tighter as you fix this down. It's a nightmare. No, I can't, with all honesty, tell somebody, go away and print that. That'll fix all your problems. It's too fiddly. It's too footery. But one of the cool things with 3D prints is that they are kind of just laminated structures. If you sit a little blade on it, hit it with a hammer, you can just crack that thing in half. And so that proved that if I could build this as a kind of a two-piece project, but still maintain some sort of structural rigidity in it, then that might actually solve the installation problems. And so that's what came in the second prototype. And so we've got a round of castellations with a draft angle on them. The idea being that you only need to get your alignment close enough to get them to start moving. Then once you start applying the pressure, once you start tightening the nut down on it, that force will actually push down on it, twist it into place, lock it in. Bob's your uncle. It's a good one. At that point, I think I'd probably worn out my welcome with just asking chaps on the internet for free 3D prints. So I went off and sent it away for a commercial print. And so whilst I'm waiting for that to come back in the post, my first boards arrived from Osh Park. And I proved to myself that you can indeed hand solder down to TSOP 20. I'm not a great solderer by any means of matter, but yeah, you can. That board, I programmed it, flashed a blinky on it, sent some strings out over UART. In the meantime, the next round of prototypes came back. Probably can't see very well on the photo there because that was printed in a fancy engineering material because I wanted to make it resistant to oil and grease and water and all that sort of stuff. But they mesh up, it works. And so, yeah, that's not finished, but finished well enough to move on to the rest of the project. One of the things I did was I was very, very apprehensive on the STMs. I'm not an electronics engineer. I don't know how much current you can push through these things. And so for the pull-up resistor on my transmission line, I used just the wrong value altogether, far too high a resistance. And so you end up with a kind of very obvious capacitor charging curve. But one of the neat things you can do in surface mount resistors is you can just stack them up and keep soldering them. I mean, it's a bit of a bodge, but that gives you a third of the resistance because you just stack them in a ladder. It works, and you square off the signal. And so at that point, again, this is talking to the community. Another chap reached out by email because I've been blogging and on Mastodon as I've been building this project, and came out and said, that's great, but could you build something smaller? Could you make it fit inside of the frame tubes on the bike so that it's kind of completely hidden and secret? And unfortunately, I don't think that the TSOP 20 footprint off the chip would actually fit in there. But what I did work out is if you have your old shifter and you rip out the motor from it, the space the electric motor took up is almost probably enough that you could fit a circuit board in there. And so shrinking things down, yeah, making it work, sent that off to JLC and crossed my fingers. So hardware's done, back to the software. We worked out that it was probably sending 9600 baud serial of some form. So what I did was I went out, rode the bike lots, collected loads of packets off the back and forth, stuck it at the bench, collected more packets, fired them into pulse view, which then gave us this, which is something that's quite, it's got a structure to it. The top is the request packet, the bottom's the response frame. They've got a shared header. They've got some really weird high value numbers at the end of it that look probably like a checksum. Maybe that's an indicator of what the protocol is. So I fired it into a checksum checker and it came back and told me, yes, you're looking at a probably Modbus. It's like, well, that's interesting. I've never heard of that, but I'll go away and work it out. It turns out the Modbus is fairly straightforward. It's just you send a write, you get a response back. You send a read, you get a response back. 2,500 messages, and that's if this is one of the things I found was being a non-technical person. Excel spreadsheets are a real value to me, and pivot tables aren't just for bean counters. You can use them for signals analysis, because we've got a whole bunch of very structured data. Fire it into that, running your report. You can you can kind of tell what the data is that's going back and forth. I've been coding all of my firmware in Rust. Rust lets you turn, well, it's got a match operator, which lets you turn this sort of call and response into code really fairly simply. So then the boards arrived from JLC, tested them on the bench, tested them on the bike in my workshop. Looked like it was working. There was no complaints. And then took it out and it worked. So we've now got a certified replacement hardware for a component that is gone. And then that's the end, really. I've got kind of lessons and next steps. I mean, the main lesson is publish early, publish often, work in the open, ask people for help, ask them for advice, and they will come out. They will give you it. They will. Yeah, people want to help you. It's amazing. The community we have here around open source and open hardware in particular is fantastic. Yeah, and that's me. Thank you. Thank you so much.